So derivatives for tan. We're going to prove it using what we know with our derivatives of sine and cos. And once we've proven it, I'm going to put a box up that says the derivative of tan is secant x squared. And then you'll be able to do it directly from there. So you can use it sort of as one of your memorized things. Like you're going to memorize derivative of sine is cos. Derivative of cos is negative sine. And whenever you have those questions, you don't have to deduce that that's the answer. Now tan, because we know tan is sine over cos, we can actually figure this one out. Because if we think of tan as being sine over cos, well, we know the derivative of sine already, we know the derivative of cos already, we know the quotient rule already. We can apply all of those things and find out what the derivative of tan is. So if I use the quotient rule here, keep the bottom the same, following the notation given in the question. Keep the bottom the same, multiply by the derivative of the top. The derivative of sine is cos, minus, keep the top the same. The derivative of the bottom, the derivative of cos, is negative sine, all over the bottom squared. What happens? Well, on the top, we get just sine squared plus cos squared. I could have written cos squared plus sine squared, but I think if I say sine squared plus cos squared, you're more naturally think of that as, oh, I remember that. That's equal to something. Yes. And this is still all over cos squared x. So yes, the top is equal to 1. And if you remember that 1 over cos is secant, then 1 over cos squared is secant squared x. And we've shown what we wanted to show. So from now on, you don't have to prove this every single time you want to use the derivative of tan. From now on, you can just go directly and find the derivative of tan. So we've got a couple here just to work backwards. To get negative sine x, you would have originally had to have cos x. To get the negative 2x, you would originally needed a minus x squared, and then it could have had any number plus c at the end. Similarly here, to get a negative 3 cos x, you would have needed to start with a negative 3 sine x plus 5x plus c. So now that we've proven tangent, you can use this. You can use either 1 over cos squared or secant squared whenever you need to do the derivative. Looking at this from a graphical perspective, if we start with tangent, and we think about what happens if we do the derivative of this over and over again. Well, the tangent graph repeats itself. So we're going to get our derivative repeating itself as well. As I graph this, can you see that all my tangent lines are positive here? They're also always positive on this side. They just keep getting steeper and steeper and steeper and steeper, so that's why our graph goes up to infinity on the left here and also steeper and steeper over here. In fact, the least scary place if you're skiing on a tangent slope would be right there. That's when things aren't going super fast. But everywhere else it just gets steeper and steeper and steeper. And since it has this same thing over and over again, we have our graphs appearing like that. Now taking that into consideration, well, it sure looks like it's part of the secant graph, the reciprocal of cos. Because if we drew our cos graph on here as well, we've got our secant graph. But in order to have all of them positive over and over and over again, this makes us think, well, maybe this is, if we were just guessing by looking at that, in order to have them all positive, I could do that by putting secant in absolute value bars. So that would be maybe one idea that I have. Maybe this is the absolute value of secant. But another way to make everything positive is squaring it. Now, when we did the derivative of sine over cos, we saw that this had to be secant squared x. But just looking at these graphs, you probably couldn't say, oh, I recognize that as secant squared x, because of how it's curved a little bit wider than secant x was and blah, blah, blah. Maybe not. So from now on, when you have the derivative of tan built in, you can just automatically do secant squared. You don't have to rededuce what tan is. Now, if you forget what the derivative of tan is on a test, well, then you can off to the side on a piece of scrap paper say tan is equal to sine over cos, and I remember the derivative of sine, I remember the derivative of cos, and maybe I can figure it out from there. So now we can do all sorts of derivatives with tan. First of all, we have to look at the question and say, what kind of derivative rules am I going to have to use? Do I have functions inside of functions, or do I have functions multiplied by functions? What's happening here? In this case, tan x is a function on its own. X squared plus 1 is another function, and they're multiplied together, so it makes sense to use the product rule. Product rule says keep one the same. Multiply by the derivative of the next one. Plus, keep the other one the same. Multiply by the derivative of the first one. So for this first one, taking the time to change a 1 over tan x to a tan x to the minus 1 will make this easier. So before we do our derivative, you could do 1 over tan x as a quotient rule, but anytime you have a constant on the top, it's usually better and faster to bring the bottom up to the top with a negative exponent and then use your power rule instead of your quotient rule. Now, both of those terms have the chain rule involved. In the first one, can you see that the 2x is inside of tan? So that's why it's a chain rule. In the second one, can you see that the tan x is inside of the power negative 1? So that's why it's a chain rule. So when we do the derivative, do the outside function first. The outside function here is tan. The derivative of tan is secant squared. You keep the inside the same. Then you multiply by the derivative of the inside. The inside function was 2x. The derivative of 2x is just 2. Second one. The outside function is the minus 1. Minus 1 comes out in front. Subtract 1 from the exponent. That's just our power rule. The inside function stays the same, so we still have tan x left inside. Then you multiply by the derivative of the inside function, and we get secant squared at the end. So, all right, implicit differentiation. On the left, the derivative of y squared will be 2y times y prime. On the right, we have a chain rule. The 7x is inside of tan. Outside function's tan, so the derivative of tan is secant squared. Keep the inside function the same. Then multiply by the derivative of the inside function, which will just be 7. To find y prime, we just have to divide by 2y. And there we have it. We have the chain rule again. The sine x function is inside the tan x function. So the derivative of the outside function will be secant squared. Keep the inside function the same. Then multiply by the derivative of the inside function. Can you notice that this is different than that? That would have a product rule. There's no function inside of another function because there's tan of x times sine of x. But here, you don't have anything with the tan, so that means all of this is inside your tangent function.